So let's continue. So last time we discussed conditional expectation as sort of the L2 projection. And I tried to emphasize this a little bit. If you have questions, please feel free to ask. Yeah, so you went through this idea that there is a L2 space of functions, and like we can think of the conditional expectation as the best approximation in this function. There is a subspace of this L2 space of functions, which is let's say I have a random variable x. I can look at all the functions of x, and then I want to predict y by choosing one of these like members of this class, and the projection idea tells us that there is a unique projection in this L2 norm, and that unique projection is called the conditional expectation. So it's the closest one to y among functions of x. So this view is very useful as we go along, try to argue some of these results. Let's say, for example, the first application was when we tried to prove this result, a complete sufficient statistic is minimal sufficient. We pick a minimal sufficient statistic u, and we want to show that t is a function of u. So the best guess of let's say us for t in terms of a function of u would be the conditional expectation of t given u. So if you want to show that t is a function of u, we first look at the conditional expectation of t given u. That's always there, and then try to show that that actually coincides with t. So that's a strategy. If you want to show that something is a function of some other variable, you look at the conditional expectation. That sort of has to be the best approximation in the sense that we discussed, and then try to verify that that's actually equal. So the completeness came in. So just to point out, this is going to come out, or like we're going to see this idea several times, that if you form this conditional expectation, and if the random variable that you're conditioning on is sufficient, then this conditional expectation would be a valid statistic, right? Do you remember this? Maybe someone tells me why that was the case. So if I have u sufficient, and then I condition some other statistic t on u, this is a valid statistic, which means it's just a function of data, not the parameter. It doesn't depend on theta. So why was that? See if you guys follow. U is sufficient, t is a generic statistic. This conditional expectation does not depend. So when I say well defined by sufficiency means does not depend on theta. Statistic is by definition something that only depends on the data. So
because u is because the condition expectation is in space spanned by the u. So if u is already not dependent on the theta, so the condition expectation will also depend.
So u is not going to depend on theta for all the statistics. It doesn't have to be sufficient, right? So it's not that u doesn't depend on theta. Its distribution potentially depends on theta. The distribution of t also depends on theta. Why the conditional expectation of t given u does not depend on theta? That's the question. Right. Yes.
Because u is minimally sufficient and t is a function of minimal sufficient statistics. So
No, I'm not assuming that t is a function of minimal sufficient statistics. So the question here is like u, like t is any statistic. T is any statistic, and u is a sufficient statistic. Then expectation under theta of t given u does not depend on theta. And because it's a function of u, that function of u, whatever it is, let's say gu, that will be a new statistic because both u and t are functions of x, so this is going to be a function of x. Yes.
I thought it was just like the definition of a sufficiency is different, right? Like you condition on U, then the distribution no longer depends on theta, so we're taking an expectation over
Yes.
distribution that there's no dependency. on
Yes,
theta.
yes, that's the point. So that's exactly the reason. So all of these are functions of x. So this is u. Once I condition on u, the distribution of x no longer depends on theta. Okay, so we were talking about conditional expectation, but it matches what we previously talked about. Conditional expectations, like or match with the conditional distribution. So the conditional distribution x given u does not depend on theta. So when I compute the conditional expectation of t given u, because that's a function of the distribution of x given u, that shouldn't also depend on theta. Yes.
Just one clarifying question. The sufficiency definition says that like the distribution of data doesn't depend on data after
Yeah.
conditioning, but
Yeah.
I suppose you could extend it say the distribution of function of the data also doesn't depend on data, right?
Yes.
Okay.
So is that okay with you, or is that the question? I suppose. So is that reasonable? Yes.
I guess the distribution of the function of the data, like, comes explicitly from the distribution of the data. You're like, you have a distribution and you put it forward through the function of the data.
Yeah. So let's say if I have conditional distribution of x given u, it just completely specifies the distribution of t of x given u for any function t of x. So measure theoretically, it's a push forward distribution. Like intuitively, t of x is a function of x if I know the distribution, like elementary probability can do the rules of transformation of densities, right? So it's just a way of like redistributing mass. So if this doesn't depend on theta, then will not depend. Okay, so there is this x implicit here, right? So everywhere that we write if you want. So if you make this explicit, it becomes more clear. So E theta of t of x given, let's say u. So this x given u distribution does not depend on theta. So t of x given u also does not depend on theta. Okay, so the only thing that you need here is sufficiency of u and the fact that t is a statistic. Okay. So hopefully this is now clear. Yes.
Could you repeat one more time why the distribution of x given u doesn't depend on theta?
That you tell me. That is not always true, but there's an assumption that you're making here about u. Right.
Yes, like, well, we know that u is minimal sufficient, so it.
I'm just
that
assuming
doesn't
that's
depend on
sufficient.
theta.
Yes, I'm just assuming sufficiency, not minimum sufficient. Right. So once I assume sufficiency, that's good enough. So once I assume sufficiency, that's the definition of sufficiency. The distribution of x given u does not depend on theta. Okay, that's like does not depend on theta by sufficiency of u. Yeah, if it's minimal sufficient, you have extra information, but sufficiency is enough. Okay. Good. Any other questions? So we're gonna see this multiple times. The next time I ask, hopefully everyone knows about it. Okay. So that's one way. Another way of like using that idea is to show this result. T is complete sufficient, V is ancillary, then T and V are independent. Again, V ancillary means the distribution does not depend on theta. To show that T and V are independent, I had to show some sort of a result like this. And this will, like, again, is going to be a valid statistic by sufficiency of T. So there we use that and then completeness. So I'm not going to go over this. And then we talked about this example, which is a classical example. If you have a normal, let's say, location family, and if you apply the Bazou's theorem, so theta is parameter sigma squared is fixed, so this is unknown. Now, if I had the average and then I subtract it from all the xi's, then this is going to be ancillary, and the sample statistic. Sorry, the sample statistic. Yeah, so this is going to be ancillary. Sample statistic is a function of that, and so that's going to be ancillary. Its distribution does not depend on theta, and x bar, we know that it's minimal sufficient. We're going to show, or like sort of at least give the theorem that it's going to be complete sufficient because it's an exponential family. We'll see. So x bar is complete sufficient S squared is independent, and so they're, sorry, ancillary and X bar and S squared are independent. Yes,
Last time there was a question about complete sufficiency and the fact that it implies minimal sufficiency. And you mentioned at the end that the other way around doesn't work, so minimal sufficiency doesn't imply
yes.
the existing. And I was wondering if there's a version of Bazoo's theorem, where you can, instead of having this complete sufficient, T will be a minimal sufficient, and then you can show that any absolute will be independent.
I don't know about such here. If it was there, they would replace complete sufficiency with minimal sufficiency because that would be a better theorem, right? So maybe there is something out there with additional constraint, but you can't really like remove it with minimal sufficiency. I don't have an example, but if you are interested, you can try to construct an example where you have a minimal sufficient statistic and an ancillary statistic, and they're not independent. Yes. Generally speaking, these guys were good. So if it was possible to reduce it, they would. So my guess is that's not possible. Okay. Any other questions? So now I want to go back to the idea of the risk and then see some of these results connected back to the risk. So there's this result, Rall-Blackwell theorem, that says that sort of or ties risk minimization with sufficiency. So sufficiency so far has nothing to do with risk, right? So we define it in terms of conditional distribution and like sort of independent of whatever loss function you put on your when you set up for your decision problem. But this is a nice result because ultimately, like at least we started from decision theoretic framework, we care about decision theory, so we care about like the risk. So does sufficiency can it like tell us something about the risk of it? So in order to state this result, Rall-Blackwell's theorem, you need to understand the convexity. So it's something about convex loss functions. So let me ask you, do you know about convex functions? How many people know convex? Okay, a lot of people. So what is a convex function?
Functions below is secant line.
It is, sorry?
The functions below is secant line.
Secant line. Okay, yeah. So what is a secant line?
You draw 2 points and make lines between them.
Okay, so you have this function. This is like x. This is f of x. This is the graph. You take 2 points on the graph and then you connect them. So the values in between, like the values of the function in between these 2 points stay below that. Okay. Any other definitions?
Second derivative is non-negative.
Sorry?
Or second derivative is non-negative.
Second derivative is non-negative. So if it's differentiable, the second derivative would be non-negative. The first derivative would be monotone, increasing, let's say. So this definition so what was your name again? Wayman. Okay. If I'm Wayman mentioned, this is exactly this definition that's written here. So if you look at like X and Y, so if you interpolate, let's say linearly between them, this would be like X lambda. So if you look at this, imagine this is called the convex combination of X and Y. So lambda is a number between 0 and 1. So call this X lambda, let's say. So as I vary lambda from 0 to 1, at 0 it would be Y, and then moves towards X. So it just traverses this entire interval. So this X lambda is moving in that interval. And then the value of the function at that point is this. So if this is below the other value, which is this red one, so this red one is the value of that secant. So that's, you can verify that that's going to be this guy. So this is going to be above the value of the function, right? So that's that definition, formally written down. And if the inequality is strict, except at the endpoints, but for anything in between, it's strict, then it's going to be called a strictly convex function. Okay, so something like this, where there's like a curvature, it's going to be strictly convex. An example which is not a strictly convex, can you tell me an example or specify a function that's not like convex but not strictly.
Affine function for line.
Yeah, so this is the simplest one. I was hoping for something more fancy, but this is correct. So a affine function is convex, definitely.
Function of flat bottom.
Flat bottom, yeah, so this is like something like that. Right, still convex, yes.
One norms.
The L1 norm, right? So that's like probably the favorite kind of function. So if you're a statistician, the L1 regularization. So this is a convex function, but it's not. So this is like the x, right? Absolute value of x. That's the L1 norm, and in multiple dimensions would be the sum of the like the absolute value of the coordinates. So it's not strictly convex, right? Not strictly convex because, for example, here, if you take 2 points here, like the secant sort of matches the function itself. It's also non-differentiable at this point, so it has nice features, enough complexity to. So, for example, it's not the everywhere differentiable. Right? That's fine. Good. Everyone knows like now convex functions. There's another like definition which I like personally, which is related to convex sets. So what is a convex set?
You draw lines, the lines stay inside the set.
Right. So if you have a convex set, if you have like pick 2 points and then connect them by a line, this line segment entirely lies within that set. So this is a little bit more geometric. So this guy is not convex because I can take these 2 points and then connect, and part of that line segment is outside. So convex, not convex. Questions? No. Okay, so now you can use this if you know convex set. So a function would be convex if the so-called epigraph is convex. So if you look at the set that's like everything that's above the graph, if that's a convex set, then it would be convex. So that's the link between convex sets and convex functions. So this is called the epigraph of the function. That sort of helps some of the arguments if you do convex analysis. Okay, so everything fine so far. So this Rolle likelihood is a statement about convex loss functions. So for example, if you have this loss function, which is theta minus a to the p, if p is bigger than 1, then this is going to be strictly convex. If p is exactly 1, that would be the L1 loss. It would be exactly like this, shifted to let's say theta. And if p is strictly less than 1, then it would be non-convex. Okay, so the statements we mentioned would work for these 2 cases: strictly convex and convex. So p is bigger than or equal to 1. Okay, in particular, quadratic loss is convex, so it's strictly convex, and so everything that we we'll talk about will work for this. Okay. Okay, so we need one more ingredient, which is Jensen's or Jensen's inequality, whatever you want to call it. So how many people know this inequality? Okay, a lot of people. So what is, let's not show it. What is this inequality saying?
Like the average of convex functions unfolded down in the variable. I can't remember which inequality is bigger than or the smaller than the function composed of the expected value.
Right. That's exactly it. So I'm going to tell you how to remember which way it is. But so if you imagine this definition of convexity, this statement is already like a statement of Jensen's inequality for a very simple case. So if you have a random variable that takes values, let's say x and y, x with probability lambda, y with probability 1 minus lambda, then what this side is, what is this side? This is f of the expectation of x, So that's exactly the expectation of the x is inside. And what is the other side? That's the expectation of f of x, right? So this is saying this is less than the expectation of f of x. So what Jensen is doing is just generalizing this equality to any, basically any distribution on x. Okay, almost any distribution. So by induction, for example, you can like extend it to the case where there are like x takes like not two values but k values, but then you can also extend it beyond. But it's a very like natural way of extending this result, and you can actually prove it rather easily without induction. I'm going to mention the proof. So this is the formula statement. If you have a function which is convex and consider a random variable x concentrated on some set S, which here we mean the probability that x belongs to that set is 1. X is integrable, and we want x to be like f to be convex on the set on which x is concentrated. So if x does not put, like the distribution of x does not put mass on some part of the space, it's fine if the function is not convex there. Intuitively, it should be clear. So then that inequality holds. Okay. So the easy way of seeing it is like whenever you pull the expectation out, it gets bigger. That might be harder to see, but everyone knows what the variance is, right? The variance is positive, and the variance, hopefully, this is easier to remember. This is, if you're a statistician, you know that the variance is something like that, right? Like this has, and then this is positive, so this is an instance of the Jensen's inequality. Forget, if you remember the variance, you remember which way it goes. So x squared is a convex function. So if you apply this result to this function, it tells you that the variance is non-negative, which is good. Okay. And then if it's strictly convex, then the inequality holds. Sorry, if f is strictly convex, equality holds if and only if x is constant almost shortly, in which case it has to be equal to its expectation. So for a strictly convex function, the inequality would be strict if x is non-trivial. So it's not a constant random value. Any sort of strange behavior, a little bit of mass there, a little bit of mass here, then this would be strict, which is pretty strong type of result. Okay. So how do we prove this? There's this very general proof that you can do that relies on the existence of a supporting hyperplane. Okay, so if you can prove, like intuitively, it's sort of clear that if you have a convex function, so for example, if it was differentiable, another way of characterizing convexity is that it stays above its tangent line, right? So if I have a tangent at any point, if the function is convex, it's going to stay above its tangent line. And so this tangent line is also a supporting hyperplane. Supporting hyperplane means that it touches the function at that point, and the function is to one side of it, like to the side above, basically, in this case. So this holds even if the function is not differentiable. So for example, if I have something with a kink here, at this point, there is no tangent, so the function is not differentiable, but there are supporting hyperplanes. There are many of them actually. So any of these would work as a supporting hyperplane. So it's supporting because it touches the function at that point, and then look at one side of it, the function is entirely on that side. So these exist for convex functions under very general assumptions and in very general spaces actually. So this result you can extend to, like, functional analysis to spaces that are infinite dimensional even. So, but assuming that there exists, so the function is such that we're in a space in which the function is convex and there exists a supporting hyperplane at x naught, which is the expectation of x. So take X naught to be the expectation, I'm going to assume that there is a supporting hyperplane. So generally a supporting hyperplane, this is the equation of a hyperplane. Okay, so a hyperplane in, let's say RD can be written as A times X plus B. Okay, that's the inner product. Like if Euclidean spaces would be A transpose X plus B. So this being equal to like something. So this is the equation of an affine function. This setting this equal to like a number that would define a hyperplane. Okay, saying that this is like, for example, bigger than some number bigger than 0 would be like this, something like that. So I'm going to construct a supporting hyperplane like this. So the way that I've written it, it's just this form, but I've added this shift here so that I know that at X naught, because this is going to be 0 and this is equal to X naught. So this is really a supporting hyperplane. And there's going to be some A that I can choose that's going to be the normal to this hyperplane, such that when I sort of vary this A, I can find an A such that the function is entirely to one side. Okay, so for example, I can make sure by choosing a property that f of x is always bigger than a of x. That's the supporting hyperplane business. And then at x naught is equal to x. So if there is a supporting hyperplane, which is under very general conditions, then I have this inequality. Okay, so I can find a function ax that's sort of below the function everywhere except at that point in which it's equal, like, touches the function. So that's the touching part. Okay, so if something like that exists, because it exists for all the x's in S, but I'm assuming that this is the function is convex on S, I can plug in the random x here. Okay, when I plug a random x, this still holds with probability 1 because x takes these probabilities, these values probability 1. And then I can take the expectation of both sides, right? And the inequality does not change. So why is that? Because of this. So expectation is a monotone operator. So if you apply it, you preserve equality, okay? Inequality. And then expectation is a linear operator. So if you apply, this is sort of a linear plus constant, so it moves in fact. So if you apply x, so this is expectation of inner product of a and x minus x naught plus f of x naught. This moves past, this is like a summation basically. This moves inside, right? Because it's a linear function. So this goes inside and then x naught is constant, comes out, and then the other thing is also come out. Okay. And this guy is by definition x naught. So this whole thing so evaluates to f of x naught. Okay. So expectation is monotone, expectation is linear. By definition, this is going to be like 0, and then this is going to be f of x naught. And this is nothing but f of expectation of x. Because x naught is the expectation of x. So it's like 3-line proof, relying on the fact that there is a supporting hyperplane, expectation is monotone and linear. Okay, sounds good. Okay. So we prove Jensen's inequality, and then if you have a strict convexity, it means that this is going to be bigger. The inequality would be strict except at x naught. So for any x that is not equal to x naught, this is going to be strict. And if the function, if the x does not satisfy this, so it's not constant almost surely, it means that the probability that it does not equal this is the mean, right? So the probability that it does not equal to its mean is positive. So there's positive probability that's not equal to that. And so this statement, because this holds on this set, it's going to have positive probability. And if it has positive probability, when you take the expectation of both sides, you preserve the strict inequality. Okay, I'm not going to go into that much, but there's a positive probability that the strict inequality holds, and so when you apply expectation, you get a strict inequality. So unless this, so if this holds, then the equality is strict. The contrapositive is that if this is equal, then that has to be equal to its expectation probability 1. This part, it's fine if you don't follow. If you follow, great. If not, just the proof of the original one, and then let's accept this part as well. And so that's Jensen's inequality and its proof. Any questions? Yes.
This might be a dumb question. I guess if you're on the expectation is monotonic operator,
Yeah.
Yeah.
So what's the question?
is that the case? Or do you need any restrictions on the function, like expectation is always monotonic?
It is monotone, yeah, always. Yeah. What this means is just expectation of, so if x naught is bigger than or equal to 0 with probability 1, then the expectation of x is bigger than or equal to 0. That's all you need. And then if x is bigger than or equal to y, then you can move around. Okay. So if you take the expectation of something which is always, almost always not negative, it can't be negative. That's the intuition. Questions? Good. Now we get to the statistics. So recall the decision theoretic framework. We had this loss function, and we had a decision rule, and then we had the risk, which is the expectation of the loss of that decision rule. So if you want to write in more details, this is L of theta delta x, right? And x is distributed like p theta. So there's some underlying probability model that this is coming from. Okay, so what is Rao-Blackwell? So the theorem says that it's a statement about a sufficient statistic. So not necessarily minimal, not necessarily complete, just any sufficient statistic. So if you have a family and T is sufficient for the family, T is a statistic which is sufficient, delta X is possibly a possibly randomized decision rule. I'm going to talk about what possibly randomized means, but includes deterministic rules that we have seen. So for now, you can think of it as the usual decision rules that you know. And then the loss is convex, let's say in the action for all theta. So quadratic loss, for example, works. We can define an estimator. So we have a sufficient statistic, we have another statistic. Like this is a decision rule, but when I apply it to my observation, it's another statistic, right? So we have two statistics, and I can condition delta x on t. So we know that if you follow what we discussed, this is going to be a function of t. It's like this approximation of delta x in terms of t. It has the other interesting property that it does not depend on theta. So it's a valid statistic and a valid decision rule, because in the end, it's going to be a function of x. So why it doesn't depend on theta? Yeah, what we said before, because t is sufficient, this is going to be the delta x is a function of x, and distribution of x does not, condition on t does not depend on theta, then the distribution of delta x condition on t does not depend on theta. So this is a valid estimator. So this is sometimes called Rao-Blackwellization, basically conditioning on sufficient statistic. You Rao-Blackwellize the decision rule. So what the theorem says is that if the loss is convex, the risk of this new estimator is going to be always as good as the risk of the original. So by conditioning on a sufficient statistic, you recover or construct a new estimator whose risk is as good as the original one. And if the loss is strictly convex, then the inequality would be strict. Unless eta is equal to delta, unless this new estimator is the same as the original one. So this is, as you can see, like coming from the Jensen's inequality, and it's very interesting because, for example, quadratic loss is a strictly convex function. So Rall-Blackwell says that for quadratic loss, if you do this, and it turns out that the new estimator after this procedure is different than the original one, it's going to dominate it everywhere strictly. So it makes the original estimator delta inadmissible. Okay. So when is this the case? When is eta equal to delta? Sorry. Yeah, so this is the case if this is equal to delta, it means that delta originally was a function of the sufficient statistic itself. So I could have written it where it was already written as a function of the sufficient statistic. There is a piece that can't be, this operation would take it out and you get it listed.
Can we say anything about this statistic being minimally sufficient?
No, there is nothing about minimal sufficiency. So this is just something about a general sufficient statistic. We just know that this is going to be a function of that sufficient statistic. It doesn't tell you about minimality, and it's interesting because it just works for any sufficient statistic. It's a pretty interesting, actually, application, simple application of Jensen's inequality. The significance is that it tells you what I mentioned. If you remember, we looked at sufficiency because of the compression, but it also tells you that statistically it's good to discard the information, because if you don't discard the information, your loss can be improved by discarding the information. So this you can think of as you're basically averaging out over the nuisance part of your data over the values of t. So there is some sort of randomness in the decision rule. Let's say decision rule, and like there is variation. So once I specify t, if delta is exactly a function of t, it will be deterministic given t. So once you specify your sufficient statistic, if there is no randomness left, then you're in the situation that eta is the same as delta. If there is some randomness left, it means that your estimator like picks up other parts of your data other than t. And this is saying let's average over those variations for each value of theta, so that you get a function of theta, and this is going to be better. Averaging out the parts that are not relevant would improve your statistic, your early decision. Yeah, so if this part is sort of like a weak dominance, like if you remember, so this is as good as delta. So if this happens, I really don't need delta. But it could be that they're equal. If this inequality holds, and at one value of theta it's strict, then theta would make delta inadmissible, because that would be as good as delta everywhere, and at one point is strictly better. So then we really can discard delta. So this is saying that if the loss is strictly convex, and if eta is anything other than delta, then this would be strict everywhere. So it's like very severe domination. Okay. So in that case, definitely eta would be, so delta would be inadmissible. And this would be like the certificate for inadmissibility of delta. Okay. Yes.
It's not necessarily still sufficient, is it? Right, like this new function.
Because let's go through the proof. I'm going to come back. So your question is that it's not necessary that t is sufficient.
No, that AOT is the new estimator.
Oh, the new estimator is sufficient.
It is. I don't.
No, that your question is that it's not necessary or it's not clear if eta of t is sufficient, right?
Yeah.
So what do you guys think? Yes.
Well, your decision rule could always just be a constant, so there is no guarantee for sufficiency.
And it's a
Yeah,
function
but
of
it's-
t, so it loses information. It does not have to be it's not a sufficient statistic.
Right. If it was a general function of t, then it would be really easy to answer that question, right? Because constant functions are functions, so it loses information. But there's a particular one, I'm taking the expectation. It's not any function, right? So take the expectation, and can it be that eta of t is still sufficient? It's a good question. Yes.
But if delta is constant, then in particular it's constant given to, and then eta is going to be delta. and
Okay.
it's still constant.
Great. So that seems to answer the question. So delta is not necessarily a good estimator, so delta could be constant. So if you do this, then eta t would be constant. Right, so it beats the original one. It just has to beat the original one. It doesn't have to be like the best. So the answer then is no. Good, so not necessarily sufficient. It just tells you that you can improve delta. Delta might be like a useless statistic or like decision rule, but you can improve, yes.
So like theoretically, maybe not practically, you had like multiple different sufficient statistics, neither of which were functions of each other.
Yes,
And you tried to like run some sort of like alternating minimization procedure in this way, like is there at least theoretically cases where that does something interesting?
alternating minimization,
So you,
okay.
like, condition on one, get something. Condition the result on the other one, get something else. Condition.
That's interesting. Yeah, so that's actually very interesting. I haven't thought about it. So this is like, if you think about conditioning as projection, it's like alternating projection. So you're projecting basically, if things work out, it would converge the projection onto the intersection. Yeah, and the intersection is what? Like in this case, so the spaces are spaces of functions of these. So the intersection would be something which is a function of both, right? So it's like you would go one level like towards the minimal sufficient statistic, it seems, right? So if you have, so what he would do probably is, it's a very interesting thought experiment. We can think about it, but so you would have like this, they call this eta 1, and then you like project eta 1 onto t, you get, I don't know what we should call it, eta 1 prime. And then project it again, I get, let's say eta 2, which is eta 1 prime projected onto t1 and so on. So this sequence, my guess is that you get at eta 1 prime, eta 2 prime, to eta 2 prime. This would probably converge to the expectation of delta conditional on t1 and t2, if like everything works out. And
yeah, I think you could argue that fairly easily if it was strictly convex, because like this is I mean, it's like a non-decreasing sequence of real numbers that's probably bounded below by 0, right? So it's going to converge to something, and as once it converges by like the strict vector, like it would have to already be like measurable with respect to those two.
yeah, I'm not worried about measurability. Most likely, so this is not correct. T1 and T2. I think what would happen is like the intersection of the space is like with the intersection of the sigma. So it's going to be a function of both, right? That's what I don't know how to write it, but it's something that can be written as a function of T1 and also a function of T2. So it's like in terms of the hierarchy, it would be like below them, but it should be interesting. I don't know what we can say about it. The convergence is one issue. Like, statistically, is it most likely better than both, right? But not better than both, definitely better than the original one, probably. But so your concern was the convergence. You try to argue the convergence of it.
If you have strict convexity, then you could argue convergence fairly easily.
Yeah, I mean, you could, I think, argue like convergence by just the fact that it's alternating projection, and like the general results that you can show that if you do alternating projections, it would like converge to. It's a famous algorithm.
But do you need like the sets that you're alternating between to have some nice property?
They're linear spaces here, so you're basically projecting onto like these two spaces that you're projecting are linear subspaces L2. So it's just projecting onto the intersection of the linear. And they're close, everything should work out. But statistically, the question is like, it converges to something, which is, let's think about it. It's a very good question. Maybe at some point I'll assign a homework problem on it. But it's a very good question, yes.
So I'm just a little confused, like, why would it be an intersection? Aren't you gaining information from both T1 and T2? And if you just.
No, you're actually losing, like, every time you do this, you lose information. You average over like some part, it's like an average. So if you remember the projection idea,
Oh, yeah, I see it.
so that's why I say projection is very useful, because you would have intuition. So this would be similar to,
So then if you continue projecting over enough, wouldn't you eventually just be conditioning on all of your data?
no, so that's the thing. So like, this is like L, this is like all the functions that can be written as a function of T1 for some G. This would be like L prime, or like L1, this is L2, which is all the statistics can be written as, let's call this H. H of this for some H. And what happens is that delta is here, I'm gonna project it here. I get this, let's say maybe that's the 0. So that would be my vector. Think about vector space. So that would be like eta 1. And then I project it back onto this. I get that, and I project it back onto this. I get this. So I'm going to alternate between these, and I'm going to converge. This is not going to be 0, but it's going to be something which is on both of them. So it will be on the intersection. It should converge to projection. It shouldn't be here, but this is going to be the projection onto. Yeah, so it's going to be like something like, imagine 3-dimensional space. This is going to be like a line here, right? These are like subspaces. And so in the end, you get here, which is like the projection of this onto this line. So you end up being a projection, like finding a projection. So it's going to be like the best approximation. So these are going to be functions of both T1 and T2. Yeah, I'm not sure how to like. So all the random errors can be written as both a function of T1 and a function of T2. That's another subspace. So that is what this is going to be, a projection onto that. And so it loses more information as you do this, because every time you do this, you lose some information in this component. And this is going to have less information to project onto each one of them. But you can follow through the argument, like the statistical argument, see what is the result. And it's an interesting thought experiment. Does that answer your question? You don't get more information, you get less information. Yes.
It seems like they're like, say, like to make the argument easy, like those subspaces that were thought, the first projection went down, there's only zeros for everything else, right? You only projected once onto a set of orthogonal.
If they're orthogonal, but there's no reason why they have to be orthogonal, right?
If there's nothing in like the set of, say we have like a bunch of different sufficient statistics, they wouldn't have to be mutually orthogonal or orthogonal.
I don't think so. No, there's no reason a priori that would happen. Yeah, just pick two sufficient statistics. There's no reason. Yeah. In particular, one could be like a function of the other one. So it could be like lying inside the same subspace, right? So you might, there's a minimal sufficient statistic and something which is not minimal. One is a function of the other. So these subspaces would be nested. Yeah. Yes.
This might have already been discussed. Like, does this continue to reduce the risk at each step? I don't see that. Because I feel like you've already removed the information of data after you've done it once. Right, so like how could you reduce your risk further?
It seems like this suggests it would do, because I can compare like eta 1 to delta. So it's going to be below the risk of this. And then I'm going to project it onto this. So the risk of this is going to be below eta 1.
But I mean, a risk is like some measure of data, right? Like how close we are to the true value of data. And we've already removed all the information by conditioning on a sufficiency to pick the first step, right? So how do we gain more information, get closer to data if we've already?
No, because the original sufficient statistic, so this is not the smallest, so there are still irrelevant parts. It could be the entire data, right? This is not minimal, let's say, right? So we removed some sort of, we improved it, but it might be there's still room for improvement. When I condition on the other one, I'm gonna like average over some other irrelevant part that I couldn't when I did T1. So I'm gonna remove. It's actually very interesting.
The T2 would probably have to be a function T1 or like, be like more efficient in some way?
We probably want them to be pretty distant.
Yeah, right.
Like you want to get as far away from one being a function as the other.
Yeah, if one is a function of the other, this is not gonna help because you already projected one is inside the other. But if they're different, then every time you project, you lose a bit of information.
Okay, so maybe once, I don't know how like continuing to do it, because you've already extracted like the information from one of them the first time, right? And then if you went back to it.
But it's like, okay, I mean, at least the picture. If you believe this picture, you're not gonna get to the intersection in one step, right? So when you project onto this, you lose the orthogonal component, but when you project back onto this, you introduce probably some component along the other direction. Right? So, but it seems to me at least, like if you believe this, if this is true, then you can see like it takes a while to get there. Like every time you project, you like remove something, but it's not like you're going to remain in the orthogonal to the original line, right? There's no reason why you remain orthogonal to that after you project onto a new subspace, right? There's a lot of room to vary, right? But intuitively, it's interesting. So, because it's not obvious that you keep reducing. Maybe you can think about an example for sure. But it seems like at least they're all black holes saying that it does happen. That the risk of it, because this is sufficient, this is a generic eta one. I'm doing this, so the risk of this has to be like at least equal, less than or equal. Yes.
I mean, in the case of something strictly convex, like quadratic loss, it should strictly decrease as you keep going, unless
Yes.
like
Yeah, you're talking about this.
that final line. Yeah,
Yeah.
like there's you know, like assuming that the two subspaces have like a relatively small angle between them, and it takes a while to get down. Like you should be strictly decreasing.
Yes. Yes. Yes.
The risk.
Yeah, that seems to be the case. So let's think about this. I mean, you could search the literature if there's something there. It might be worth writing a paper about. I mean, I haven't seen something like this at the level of sufficiency done. So this idea is very old, like alternating projection. But whether if you view this operation as projection, and then I don't know what happens, to be honest. So it's like this suggests that like if you believe projection, viewpoint, and roll black hole, these two suggest that this converges and converges something which has like a better risk than both. Maybe something has looked at this. Seems very natural to do. If you have, yes.
I mean, do you know like what the like so what a description of the subspace that it's converging to is? Because it's definitely like, forgive me for bringing sigma algebras up again, but like it's not it definitely wouldn't be like the sigma algebra generated by both of them, because that's a larger.
No, it's the intersection.
Yeah.
It's the intersection of the, yeah. So it would converge to the subspace found by the intersection of the sigma
Yeah,
algebra.
but is there like a more concrete way to describe that intersection in terms of the
Function.
two statistics?
Yeah, I'm not. Yeah, that's
But like not at the same time necessarily, right? It's just like I know there's two functions.
Yeah, it's different
Yeah,
functions.
yeah.
T is like the A does F1 to T1 or T for F2 T2.
Yeah, so that question goes back to like how to describe the intersection of two sigma fields in terms of functions. And it's worth thinking about, but maybe just what Wayman, what Wayman mentioned, that it's just a function of both. But it's worth thinking about. I don't know, to be honest, the better description. Right? This suggests it converges to the intersection. Yes.
So I remember when we are, like, say, if we condition on two random variables, we are saying we are conditioned on the actual sigma algebra generated by the both.
Both, yes.
But when we are do the projections, that's intersection of the two.
No, so projection is like separate. So you're projecting onto something, right? So if you're projecting onto the sigma algebra generated by both, it means that you're conditioning on both. So if you imagine what I mentioned here, this space is similar to the sigma algebra. So there's another way of, so instead of saying sigma algebra generated by X, you can say the space of all functions of X. Okay. When you say the sigma algebra generated by X1 and X2, it's the set of all functions of both of them. So like all random everything can be written as a function of both at the same time. And so if you like project onto that space, it's like conditioning in both. Right. But this is sort of conditioning on something less, like not the, like there is a joint and like a join and there's a meet. So subspaces have like a order spectrum. So the join would be like something which is like this plus that, the meet is like the intersection. So this is projecting on the meet, not the join. Yeah, this got pretty interesting, but let's you can search the literature, see if there's anything like this. Any guys, if you guys find anything, let me know. If you have thoughts, like experiments, like what the model, and you can come up with. It's hard to like calculate these in practice, but like numerically, you can try to calculate them. Like coming up with like simple examples to see what this does would be interesting, and then try to like maybe say something about it. But everything points to the fact that this is going to improve until you hit the limit. Okay.
Which somehow connect to the discussion on complete sufficiency.
It is related. So we're going to get to like something soon where like basically this, I think you could rephrase it in this way, that once you do it once, then you're done. So that's like if you have a complete sufficient statistic. Yeah, that would, we're going to get to that very shortly.
But I guess wouldn't these projections eventually converge to a complete sufficiency statistic?
No.
No,
No, there's a lot of space here. So you're just starting from 2 here, right? There's a lot of like complete sufficient statistic maybe somewhere else, like down at the bottom. So just based on 2 sufficient statistics, it's not gonna necessarily. So for example, you could, yeah, I have to think about an example, but it's just gonna improve on the whatever you initialize with, but it's not gonna get you down to completeness. Completeness is not easy to get to. Like you have to like rule out everything else to get to the complete sufficient. Yes, yeah, there. But we'll see the connection to completeness. Okay, so if no questions, let's try to prove this. The proof is very simple, actually.
Oh, I guess I have a question.
Yeah.
Delta is sufficient, is Gino sufficient?
Delta is sufficient.
Sufficiency is a property of decision.
No, it's not. So yeah, okay. So delta as a decision rule, we can, but delta of X, let's say, if you think of a delta, a value that X, that's a random variable, can we say that delta of X is, if delta of X is sufficient, any condition on sufficient statistic, then what do you guys think? I don't know. Very interesting questions, which I don't know today. Okay. So we'll leave it there. If most likely not, but if delta of X is sufficient, is eta T sufficient? I would say 90%. No? Yes.
Is it possible for 2 sufficient statistics to be independent random variables?
We can add it to the list of the questions that I don't know.
Because if, like, I mean, this is related to this, but like, so if delta and T, like delta X and T were independent, then you just end up getting like the expectation of delta, like not conditional.
Yes, yeah, so that would give you a counter example, yes.
But I'm not sure, like, it seems plausible that you can't have independent sufficient statistics or something, but then there might be a situation sufficiently similar to that where something goes wrong.
Yeah, so let's, I agree. So it would be like give you a counter example, most likely question 1, but can we have 2? These are all good homework questions for next year, independent, or this year. Independent. And we have independent, 2 independent sufficient statistics. You can think about it if you find the answer, let me know. Yes.
Can you show, like last class, that the sample and the sample variance are independent? Those are both sufficient.
One is sufficient, the other is ancillary. It's sort of the opposite of sufficient. Like one is sufficient, the other is ancillary.
Oh,
Right. That's the Bazou's theorem. Okay, so the proof is quite simple. The only place that we use, any other questions? Yeah, so the proof is like simple. What you the use of sufficiency is only to say that this is a valid estimate, a valid statistic. Okay, and we already know why that is because of the definition of sufficiency. This does not depend on theta, so it's a valid statistic. Then you can use the Jensen's inequality if you think about it, conditional on t. So everything that we mentioned here, you can condition on anything you want because it's a conditional expectation operator. It would work. So I can condition on t, for example, here. So you can say expectation of f of x given t is bigger than f of expectation of x given t. So you can add conditioning to the expectation and carry it around. That would still hold. This would be like a stochastic statement because both sides are random variable, but it's valid by the same. The exact thing is like conditional expectation is monotone and linear, so this proof would go through. So what I'm going to do is apply Jensen's inequality to this function L theta delta, but delta is sorry in the second argument. The second argument is it's convex in the second argument, so you can ignore this part. Imagine it as a function of only the second argument. I'm going to move the expectation inside, so it's going to get smaller. So that's the Jensen's inequality. And then this expectation is by definition eta. Right, so I get that the loss of this eta is less than or equal to the conditional loss of that, and then I take the expectation on both sides. Okay. When you take the expectation on both sides, you get expectation of this and then the expectation of that. So this is going to be the risk of eta, and this is going to be the risk of delta. Why?
Conditioning the expectation condition.
Yeah, this is the iterated property of expectation, excluded property of that property that we mentioned. If you take the expectation of a conditional expectation, you get the original expectation. So Jensen's inequality followed by the monotonicity. Again, you need monotonicity because you're applying expectation, which just takes this and then smooth. So take expectation, use monotonicity and smooth. So that's the proof. And the discrete part comes from the strict part of the that state, like the Jensen's inequality statement. You can try to verify that. Okay, that's Rao-Blackwell-Rao-Blackwellization, and an interesting discussion about iterated application of it. Questions? Yes.
So what do you exactly mean by delta is a randomized decision?
Oh, yeah, that's good. I actually forgot about mentioning. So what do you guys think? What do you mean by delta being a randomized decision? So this holds for like for all decision rules that you know, but it also holds for randomized decision rules as well. What do you guys think?
Guess instead of being exactly being a function, it's like a distribution. Like delta x is something like probably measured instead of a function.
Right. So formally it's like that. So intuitively what it is that I observe my data and then I flip a coin or like another source of randomness to generate a random variable and I form a function of both and I give you the decision. So I introduce external randomness into my decision. Is that clear? So you get the data, but you also randomize. So like your decision is not going to be solely dependent on the data. If you give me the same data next time, I might produce something else because I have an external source of randomness. So you can say it's I would like to maybe add a page here, but let's see if I can. Move this up. So randomized decision rules. So for example, you could have, so they like the usual decision rules are functions like from your sample space to, let's say, your action space, right? I'm going to say like omega for us, like the parameter space. You can think of randomized decision rules as like delta being a function from x times some other space to omega. So basically delta of x and u is an external source of randomness. That's one view of it. We can think of it as deterministic rule over a bigger state, but when you plug it in, you plug in your external source of randomness like a random variable. Another way of viewing it is like the same thing, but delta x is now like give you this is like the probability of it's like a probability measure if you want. So what it says is like gives you the probability. How should we? So basically what you specify is the probability that delta x is in A, something like that. So given any, yeah, it's not a very good way of stating it, but you understand what I mean. So this gives you, like for every x, when I plug it in, it tells you like, it gives you a distribution of data, okay, for every x. So if you want to be really precise, it would be like a Markov kernel. So delta would be like for every x, yeah, for every x. For every x gives you the probability of the data. Okay, so it gives you a random choice. So if you take the expectation, for example, it would be a deterministic rule, but that gives you just see if we can do a better. I would say this is an easier way of viewing it. Okay, so imagine that like I can like this is like let's put it aside. I'm gonna write it as like still write it as delta x, but imagine that this delta is a random function. Okay, so I like absorb this u into the definition of the function. So this is, that's a viewpoint. This viewpoint is better. So delta x is a random. No, so delta itself is a random function. Okay, so when I apply, there are two sources of random. It's when I apply x, because delta is random, delta x would be another random variable. So however you want to look at it, it's sort of this idea that I introduce an external source of randomness. My decisions are random. Okay, they're given the data, even like condition on the data, I have randomness. And everything would work here if you go with the, so think of the delta of x as being doubly random. There's randomness in x and the root is also random. But like delta x in the end would be a random variable, just varying because of two sources of randomness. It's just a random variable, everything works. And so what this is saying is that doing randomization is not going to help you. Okay, that's another consequence, because when I do this expectation, I'm going to average out over that external randomness as well. So this is going to be precisely a function of t, which is a function of x. So this is going to be always a deterministic decision. So from this operation, you get a deterministic decision. So Rowe Black also tells you that randomization does not help with convex loss. Okay. Yeah, this was like more complicated than what it is. So we can write it down, but it's like simple. Yes. Yeah, for non-convex, I actually should have an example which like somewhere here. Yeah, this tells you that Rho black hole can fail for non-convex loss one. We'll go through this exam. But yeah, it fails, could fail. Not necessarily, but could. I think we're out of time. Next time, we're gonna like do this example, concrete example to show that how this machinery works. Thank you.
Professor, sorry.